I will be talking about a doped triangular lattice insulator in Moiré materials. I'll get straight into the material. I think probably to this audience, I should just briefly introduce the Moiré material. In particular, the semiconductor Moiré material. The building block is this so-called transition metal dichalcogenide semiconductor. This is the cross-section structure. And if you look from top down, it has a honeycomb lattice, just like graphene, except now the A, B sublattice sites are occupied by different atoms. And the brilliant zone is the same as the graphene. And interestingly, the electronic states of interest are also located near the K and the K prime point of the brilliant zone. So it's at the zone corner for this semiconductor rather than the zone center. And this is a very simplified band structure, taking into account of spin-orbit interaction. So the absence of emergent symmetry in the system would basically, like you think of it as graphene, but then you open up an energy gap at the K and the K prime point. So there's an energy gap here. It's about 1 to 2 eV. It's a large gap. And there is also a Ising-like spin-orbit interaction. So basically, we just split the spins at each of the valleys in opposite way. For instance, this is spin up, spin down, and this is spin down, spin up. So that to maintain the time reversal symmetry, because the K and the K prime are time reversal partners. Okay, so this, it's like a graphene with a gap and a large spin-orbit interaction. So that's the building block. Oh, and for the pristine material, the Fermi energy is located inside the gap. And you can build Moiré superlattice structure just like graphene. There are two ways to do it compared to graphene. There's something slightly different here. You can use two of the same material, for instance, tungsten selenide on tungsten selenide, or maybe more recently is molybdenite on molybdenite. Is the hot choice of material, and then you make it a twist angle theta, and that typically will give you the interference pattern for the atoms. And Moiré period is usually of interest is about 5 to 10 nanometer, that kind of a Moiré length scale. Or you can actually, in this case, that's something different from graphene, is that you can use two different materials and making use of the lattice mismatch delta here. For instance, there's a 4% lattice mismatch between these two materials. Then you don't need any twist angle. You just directly put on top of each other, aligned to 0 degree, and you still get a Moiré superlattice structure in this way. And typically, it's also in between 5 to 10 nanometer Moiré period. And you can see the Moiré superlattice structure using STEM. This is actually an experimental STEM image of this type of structure that I will focus on today, molybdenite tungsten selenide, angle-aligned Moiré. And this is done in collaboration with Dave Muller's group at Cornell. And the small dots here are the atoms, but you can clearly see that on top of that, there's this interference of the atomic structure that produced this Moiré pattern. And here I just draw the unit cell of this particular Moiré superlattice structure. Okay, so the band structure is actually a little simpler compared to twisted bilayer graphene, as long as we are in this limit that the Moiré period is large compared to the lattice scale of the original material. Then you can, to a good approximation, you can forget about the original atoms and just treat the electrons with a certain band mass move in a smooth periodic potential defined by the Moiré. And as a result, you basically would just go from the band structure in the big brilliant zone to a series of flat bands in the mini brilliant zone. So you basically think of it as a zone folding picture. And you get this series of flat bands because of the additional Bragg scattering due to this superlattice structure. Okay, there is a seminal paper by Alan McDonald's group in 2018 showing that if somehow you can actually get an isolated flat band in this system, that this isolated flat band is far away from the other band. Of course, in reality, it's a little bit complicated because of the Coulomb potential can mix these different bands. But let's say that if this band is far away from the other bands, and then the low energy Hamiltonian can actually be mapped to a triangular lattice Hubbard model, that you can just think of it that each of this as like a Moiré atom, that the size of the atom, of course, is now much bigger. It's on the order of a few nanometer. And the trapping potential depth is 100 to 200 milli-electron volts. And in this case, you can think of it in a low energy scale, the electron can hop between sites with an amplitude T. And if you have two electrons on the same side, they experience an on-site Coulomb U. And there is also an intersite Coulomb B, right? And a typical energy scale for this kind of a system, T is in between 1 to 10 milli-electron volt. So the total bandwidth is in a triangular lattice is 9T. So it varies from 10 to 100 milli-electron volt for the bandwidth. On-site Coulomb, you can sort of estimate using the size of the Varnier orbital, and it's on the order of 100 milli-electron volt. And this you can use the Moiré period to estimate the inter-site Coulomb. It's about 50 milli-electron volt. So for many cases, actually, the Coulomb energy is at least comparable, and in many cases, actually bigger than the total bandwidth of the system. So it's actually in a strong correlation limit easily for this type of materials. And indeed, this is our first experiment together with Fang Wang's group also from Berkeley. We measured the resistance. In this case, it's a 2-point resistance measurement at the time as a function of the filling factor here. Let me just be clear with the notation here. Filling factor 1 means 1 electron per Moiré unit cell. 2 is 2 Moiré unit cell. And 2 corresponding to a fully filled Moiré band, and 1 is a half-filled Moiré band. So you can actually see that there are 2 clear resistance peaks at filling 1 and 2, and actually way more clear at the filling 1. And that at the time, we think that it is a Mach insulator. I will tell you a little bit more why we think that it is a Mach insulator. I hope I can convince you that it is the case. So the resistance actually diverge in the low temperature limit. Okay, so that's a first indication, from a 2-point resistance measurement that there is a Mach insulator coming out at half band filling. And another thing that's actually quite unique about this material I want to mention now is that there is this unique optical selection rule that left-handed light can only couple electron hole pair excitation at the K value, and right-handed light only for the K prime value. And if you remember the band structure of the system, the spin and the value are also coupled, so it's also selectively coupled to a particular spin for this optical transition. So actually that provides a way of measuring semi-quantitatively the magnetization in the system, because you can think of it like if I don't have any net magnetization in the system, I dope some holes into the system and I don't have any spin polarization, then the 2 channels will exactly cancel, then I get a net 0 magnetic circular dichroism or MCD signal. But if I fully polarize the holes to one particular value, then this transition is actually Pauli blocked, but this transition is allowed. So if I'm just measuring, the difference in absorption between left and right-handed light, which is basically the magnetic circular dichroism, and you can get a semi-quantitative measurement of the magnetization of the system. And I will rely on this measurement quite a lot in the following slides. So this is an example. This y-axis is really MCD, magnetic circular dichroism, as a function of the magnetic field at low temperature, 1.6 K. And you can see that it actually displays like a paramagnetic response. It just saturates at about half a Tesla. It has a slope here, and the slope actually can give us a measure of the spin susceptibility of the system. And on the right, what I'm showing is the inverse susceptibility extracted from this slope as a function of the temperature. And the dots are the data. The red line is actually the Curie-Weiss fitting. And we can actually extract a Curie-Weiss temperature in this fit about -1 Kelvin. So that the negative sign shows that it's antiferromagnetic exchange between the local moments. Remember that it is actually an insulator at filling equal to 1. And so it's consistent, at least with the super exchange mechanism, that it produces a net antiferromagnetic interaction between the local moments in this Mach insulator. Okay. All right, so, but today the talk, actually, I really want to focus on the physics of a doped Mach insulator. Of course, the physics could be really rich for doping a Mach insulator. I'll focus on, a few aspects related to magnetism. For instance, in general, about the physics of doping a Moiré Mach insulator. For instance, if you dope to a commensurate fractional filling, because of the longer range Coulomb interaction, you can stabilize this Wigner Mach insulator. These are the references. You could also stabilize pair density wave, as predicted by Liang Fu, but it has not been observed so far as I know. And I will focus more on this topic here as kinetic magnetism and spin polarons. These are a series of theoretical references predicting that you can actually get a kinetic magnetism and spin polarons in this system. And of course, you can also predict but not observe that the emergence of unconventional superconductivity, and that has to be still to be explored experimentally. But I will focus on this part, basically the kinetic magnetism. The particular material that I will focus on is actually in collaboration with Liang Fu's group at the beginning, is this AB stack molybdenite tungsten selenide Moiré. And what I'm showing here is actually the topmost valence band of the system, and there are two bands of particular interest, one actually from the Moiré orbital, which occupy a triangular lattice, and the other one, the next one actually is from the tungsten orbital, occupying the B sublattice sides of a honeycomb. Okay, so it's actually like a honeycomb lattice, but just these two bands have orbitals, each occupying a triangular lattice. And so the next nearest neighbor hopping is actually the intralayer hopping that produce the bandwidth of each of these orbital. And then the nearest neighbor hopping is actually an interlayer hopping. It's actually a bit weaker compared to the intralayer hopping. So, and this is the energy gap delta between the two bands here. So this delta actually can be easily tuned, which is equal to the sublattice potential difference between the A and the B sides. And in this system, it's easily tuned by applying a vertical electric field because these two belongs to two different layers, right? So if you apply a vertical electric field, you can produce a Stark effect, a Stark shift between these two bands. And that Stark shift is actually exactly equal to the sublattice potential difference. So the sublattice potential difference in this system is continuously tunable by the electric field. Okay, so this is at least a very simplified version of the band structure calculated by Liangfu and collaborators for this material. And of course, that does not include any interaction, but if you say you put the doping into the system that you dope to filling factor equal to 1, fully half-filled a Moiré band, then maybe the more appropriate picture to think about it is that the Moiré band is divided into this lower and upper Hubble band for the Moiré orbital. And then the tungsten band is something like this, so we can get into the insulator regime in this case. But we can also use an electric field to actually tune the energy difference between the tungsten and the Moiré orbital. And if you apply a large enough electric field, you can get into this a charge transfer insulator that is still at filling factor 1. The Fermi level is here, but now you actually, instead of the U here, you actually get a charge transfer gap delta. The next carrier you add into the system will be actually going into the tungsten layer. So in this sense, it's a charge transfer insulator is no longer going into the Moiré orbital, but it's going into the tungsten orbital. Okay, so this is the typical device structure that we study in this study, and this is the Moiré heterostructure encapsulated between by boron nitride. Boron nitride is a very good insulator, and then we encapsulate the device by the top and the bottom gates, which are just electrodes. And the two gates will allow us to independently tune the filling factor in the material, as well as the electric field, because we have 2 degrees of freedom. We can also tune the electric field that can actually tune, basically going back here is tuning this energy gap between the two orbitals from different layers. And this is a typical device structure. We can make a Hall bar and measure some transport properties, but we can also shoot laser in the center of the device and measure some optical properties and try to infer things related to magnetism. Okay, so this is the outline that I will focus on I will try to discuss 2 things. The first is actually that I will stay in this limit here. It's a Mach insulator, and I will focus on the whole doping of Mach insulator, basically doping below filling factor 1, and I will tell you the emergence of a kinetic antiferromagnetism and spin-phonon in the system. And the next topic that if I have time, I will just tell you that you can apply electric field to bring into this charge transfer insulator. And then we actually can dope, instead of holes into the system, we dope additional electrons into the system to get into the tungsten band. And we actually see emergence of ferromagnetism there. And I will try to, discuss a little bit what we think is going on in these 2 cases. Well, it's pretty clear in this case, but maybe a little less clear in that case. Okay. All right, so let me just first talk a little bit about kinetic magnetism, kinetic frustration in the triangular lattice. Probably some of you here are experts and more expert than me. We'll stay in the strong interaction limit so that U is much, much bigger than T, so that T is also much, much bigger than the super exchange interaction J, okay? And for instance, if we dope above filling factor 1, we electron dope the Mach insulator. And for this doped electron to gain kinetic energy, because there is this hierarchy in the energy scale, it costs so little energy to flip the spin. It just only costs the energy of J, but the electron can gain kinetic energy on the order of T. So that basically it's very easy to get into to flip many of the spins and then try to get more hopping for this added electron in the system. So it turns into a ferromagnet, And it's actually a very well-known phenomenon known as the kinetic ferromagnetism or the Nagalka ferromagnetism in this case. But there's something actually quite special about the triangular lattice. If you hold up the system, it's actually not symmetric. It's not electron hole symmetric for the triangular lattice because this added hole here actually has a negative T, negative sign for the hopping constant. And so in order for the hole to actually hop from this side to that side, there are two paths to do it. One takes an even number of bonds, one takes an odd number of bonds. And so if it has a negative sign for the effective hopping, it actually gives a destructive interference if the spin background is actually a ferromagnet, okay? So in order to actually reduce this kind of destructive interference so that the hole can gain more kinetic energy, it's better to have an antiferromagnetic background so that these two paths can actually be distinguished and so that the interference effect can be reduced and so that the kinetic energy of the hole can be released, right? So in this case, so it's really like to gain kinetic energy, it's better to have an antiferromagnetism. So you can sort of think of it as a kinetic antiferromagnetism for a hole doped case. It's totally in contrast to the electron case. All right, so that's a zero magnetic field. And a finite magnetic field, actually these are a series of references. It's actually first envisioned by one of the chairmen here in the audience. And also later on really work out the details by Liang Fu and Eugene Danner on predicting what you can observe actually in experiment. So we are actually following quite a lot on this theoretical references. And so in this limit that the Zeeman energy is actually larger than J, so that the external magnetic field is able to flip many of the background spin to spin up, but it's less than the kinetic energy T here. Actually, the prediction is that you can form a spin polaron that the hole can bind to a spin flip in the nearest neighbor site, such that these two paths can also be distinguished to reduce the total destructive interference so that you can gain more kinetic energy. So the binding energy here for this spin polaron, because it's a kinetic effect, is actually on the order of the kinetic energy of the electron T. Only if you apply large enough magnetic field that exceeds both of these energy scale in the system, then you can really flip all the spins around the hole, then you can actually get a bare hole in this system, okay? So that's the basic physics. And then the prediction here is actually that if you can measure the magnetization as a function of the magnetic field, and if your magnetic field exceeds the energy scale of J, then you get the first plateau in the magnetization, and that's in the spin polaron phase here. And then only if you apply a magnetic field that is large compared to the T, the kinetic energy, then you get into this fully polarized phase that is left with a bare hole. Okay, so the first prediction is that you would expect a magnetization plateau for a hole doped triangular lattice Mach insulator, and for the hole here is a spin 1/2 particle, so that the saturated magnetization should be 1 minus x times 1/2. X is the hole doping density from the Mach insulator. For the spin polaron case, it's actually a spin half because there's a 3/2 because it's the spin flip, so that it actually should be 1 minus 3x divided by 2, the magnetization. So then the next prediction is actually that if you take the ratio of the magnetization plateau, it should follow this very specific doping dependence, 1 minus 3x divided by 1 minus x. It's because of this 3/2 to 1/2 quartz particle. Okay. And finally, there are also some specific prediction about doping dependences. You should only stay at low doping range, because if you go to too much hole doping, then the spin polaron, they start to overlap, and they become something else, and you lose the signature or in the magnetization plateau. And finally, it has not been measured experimentally that it will be it's an interesting metal actually, that it's a metal that is compressible, but it actually has a gap in tunneling. So it's an interesting pseudo gap metal. All right. So then I talk about experiment. First thing I want to talk about, this is the work by 2 graduate students in the postdoc. And the first thing I want to talk about is kinetic antiferromagnetism. And we can measure the magnetic susceptibility using the technique that I told you. So this is the inverse susceptibility as a function of temperature. It follows the Curie-Weiss temperature, Curie-Weiss dependence pretty well. And then you can actually do the fit to extract the Curie-Weiss temperature. And this is the result as a function of filling. Filling 1 is the Mach insulator. it has about -1 Kelvin Curie-wise temperature, but then you can see that once you go to whole doping, you quickly get in the magnetic interaction energy actually gets more antiferromagnetic. Right? So it's very much consistent with this picture of kinetic antiferromagnetism. And then we look at the magnetization, or the MCD, as a function of the magnetic field at different doping densities more carefully. And so this is actually at electron doping, the Mach insulator. You can see pretty much like a paramagnetic response. And then this is very close to the Mach insulator. Then this is whole doping into the Mach insulator. You can see the emergence of an intermediate plateau in the magnetization. And then finally, if you dope too far away from the Mach insulator, the plateau is also gone. You can zoom into a particular doping level and then do a temperature dependence with increasing temperature to about 5 Kelvin. The plateau is also gone. So it's just becoming more like a ferromagnet. So the conclusion is actually that at low temperature, it has a plateau between 2 to 4 Tesla. And it only appears in a doping range between 0.8 to 1. So whole doping up to 20%, then it's also gone. It appears below 5 Kelvin-ish, okay. Which is pretty much on the order of, you just go below the temperature of the antiferromagnetic interaction. Right? And we can analyze the plateau a little bit more carefully. For instance, we can take a derivative, which is like a differential susceptibility of the system. You can get a differential susceptibility dip corresponding to the plateau. Then we can take that value as the value for the magnetization, and then we can also take this value as the saturated magnetization. Then we can take the ratio and plot the doping dependence, right, for the doping dependence of the magnetization ratio. And this is the result. This is the ratio as a function of filling factor. And the dashed line is actually the theoretical expectation of a 3½ particle to a 1½ particle ratio. And you can actually see that it follows reasonably well with the theory. And finally, about the doping phase diagram, is just that we pretty much observe the spin polarons down to about 0.8 filling, and over a magnetic field range that's nearly doping independent between 2 to 4 Tesla, where we actually can see some magnetization plateau. So overall, there are some, quantitative disagreement with theory, but overall it works pretty well. Okay. We can also estimate some energy scale. T is on the order of about 5 milli-electron-volt using the known G factor of the system. Okay. And one last thing I want to highlight a little bit is what if you actually keep doping the system to some commensurate fractional filling that actually the electrons are all arranged into this generalized Wigner crystal. For instance, that the electron can now arrange into a honeycomb lattice. And you actually can see that there is this kinetic antiferromagnetism coming in at the beginning of whole doping. But once you get into this commensurate filling of 2/3 here, that the holes actually, the doped holes become frozen because of this Wigner crystal, and you actually get a large suppression in the kinetic antiferromagnetism in the material. Okay. Yeah.
You were showing this Curie-Weiss temperature enhancement with doping. I'm not sure how to interpret it. I mean, so it's true that the holes, in some sense, mediate some antiferromagnetic interaction, but first of all, there are not so many of them. So one can't interpret. I would think, I should view this as an overall antiferromagnetic interaction between all the spins. You're measuring Curie-Weiss, it has a magnitude that's supposed to be coming from every electron, which is.
I'm not sure. Yeah, I'm not so sure. I totally understand what we just.
And
it's
also,
weird,
it's
yeah.
metallic in this regime, so eventually it's like there's
ferromagnetism. It's a metal, right?
So
yeah.
The interpretation, straightforward interpretation as Curie-Weiss,
Very important.
I'm not sure.
But if you have like a very small Fermi energy in the system, if the metal, then you could get a.
So is the Curie-Weiss temperature also?
Yeah. Yeah.
I mean, I think it's fairly typical in strongly correlated metals. Curie-Weiss-like behavior in metals that are not so far from being a correlated insulator, but the interpretation as a strength of antiferromagnetic interactions is sort of questionable. If you try to fit a power susceptibility to a Curie-Weiss temperature, you'll get a very large Curie-Weiss temperature.
It is true, yeah. That's just from the Fermi pressure of the system.
So there's some combination of these effects adds to it.
Yeah.
This theory doesn't take into account it's a metal.
Maybe I can actually try to answer it. I can answer it. Maybe I give you another way of thinking about it is that let's say we don't vary the temperature of the system. We go to the low temperature limit and we measure the saturation magnetic field as a function of the filling factor, and the saturation magnetic field does go up, with increasing doping.
In this audience, which is heavily studying insulating antiferromagnets, it's common to think that as you lower below some order 1 fraction of the Curie-Weiss temperature, it magnetically orders, and that's not going on here, right?
As far as we can tell,
so
yeah.
That's tells you that the physics is somewhat different, right? But it's interesting. Yes.
Okay. Pay attention on the time. Okay. For the last 5 minutes, I'll talk a little bit something different. and you can comment more later after the talk. So this is actually more like in this case, it's more like a honeycomb lattice. The doped electron will go to the other sublattice sides of the honeycomb lattice, so it's charge transfer insulator. So there's something I first want to mention about this system is quite peculiar, is that the moly layer actually has much flatter band. It experiences a stronger Moiré potential compared to the tungsten layer, which experience a weaker Moiré potential. So the charge carriers in the tungsten layer is actually way more itinerant. Okay, and so you can sort of think of it that if I have a doped charge transfer insulator in this case, I can sort of think of it, I have a triangular lattice of local moment for the moly layer, and then I dope additional itinerant carrier to the tungsten layer. It's actually very close to a Kondo lattice model. In this case, actually, we have a recent experiment showing that there is the emergence of a heavy fermion behavior. In this case, that we have a lattice of local moment, triangular lattice of local moment in the moly layer and in the itinerant carrier in the tungsten layer. Okay, so it has connection with heavy fermion physics. That's one thing I want to say. And the second is that you can, of course, in this kind of system, you can tune the filling factor very continuously. For instance, we can tune the filling factor in just the itinerant layer continuously, and this is actually the experimental measured or determined or estimated Kondo temperature or the coherence temperature for the heavy fermion. And you can actually see that it just drops continuously with a decreasing doping density in the tungsten layer. And it seems that it's actually going towards zero at some finite doping density. So it's an interesting question to ask what would be the magnetic properties near this point that, we start to not have the heavy fermion. So that would be what we are going to see. So the quick answer is actually that we observe magnetism coming out once we go below this filling factor. We observe the emergence of ferromagnetism. This is the Hall resistance as a function of magnetic field measured at this particular doping density. And then you can actually see a clear anomalous Hall response, and which disappears at about Tc of about 3 Kelvin. And this is basically as the same Hall response as a function of filling factor at different temperature. You can actually see that the anomalous Hall signal goes away at about 5% doping in the itinerant layer. Okay. And we can also use the same measurement as we have done using the MCD to try to get a sense of the magnetic properties of the system. So this is the magnetic susceptibility as a function of the filling factor only in the itinerant layer. And you can actually see that there is a big enhancement in the susceptibility, peaks at around 3% doping. It starts to go up quite high at below 5%, but it peaks around 3% doping. And once again, we have nothing better to do. We do a Curie-Weiss fitting to it, and it actually, you can get a positive Curie-Weiss temperature around this filling factor here. Okay. And so it actually, both the transport measurement shows that, you have a clear anomalous Hall response, but also the Curie-Weiss temperature is actually positive. So everything is quite consistent that there is ferromagnetism coming out at the filling factor below 5%. And there's one more thing I actually want to mention about this transition at 5%. So there's a magnetic transition from a paramagnet to a ferromagnet. But at the same time, there's actually a metal insulator transition going on, going from a heavy Fermi liquid actually to what we believe is the Anderson insulator. That is because of the mobility edge is about 5%. And we get actually into an insulating state, which you can actually see here. Is the coherence temperature pretty much decrease all the way to 0 as you get closer to 5%, and then boom, it just becomes like an insulator. So the magnetism, the ferromagnetism, and the metal insulator transition seem to occur at around the same doping density, as far as we can tell. So with that, here we try to summarize what we know in terms of this phase diagram here, which is the doping density in the itinerant layer. And you can actually see that the anomalous Hall, the spontaneous Hall response coming out below about 5% here. And that's actually going into an Anderson insulator. So it's a ferromagnetic Anderson insulator. And the Curie-Weiss temperature is actually positive over this range, about 0 doping to about 10% doping. Okay. And the red dot here is actually the estimated Kondo temperature, or the coherence temperature scale. It's just continuously dropping towards this point. And finally, we also try to extract the t-square coefficient, which is proportional to according to the Katawaki's Wood scaling, is proportional to the effective mass of the itinerant of the heavy Fermi liquid, and that seems to be showing a effective mass enhancement as we tune towards that critical point as well. Okay, I don't critical point or crossover, but yeah. So this is basically what we know so far for this system. All right. And that's, you know, that's pretty much that part. So this is a summary and outlook. We have I hope to convince you that, you know, for whole doping of Mach insulator on the triangular lattice, we observe the spin-phonon and kinetic antiferromagnetism. Actually, there are recent AMO experiments also by measuring the spin correlation function. They can also observe in a sort of short distance high energy physics that there is also spin-phonon coming out from a whole doped triangular lattice Mach insulator. And for electron doped charge transfer insulator, it's probably more complicated. There's some connection to heavy fermion physics and also disorder. What kind of mechanism that's driving this ferromagnetism is rather unclear at this point. Can it be kinetic? Can it RKKY? Or can there be spin-phonon as predicted by this reference here? Maybe we can actually look at the magnetization as a function of magnetic field more carefully to search for a plateau, for instance. And yeah, so that's pretty much what I want to say. And with this, I want to acknowledge the people. This work is in collaboration with Ji Shan's group at Cornell. And these are the graduate student, 2 graduate students and the postdoc involved in the work. And we just benefited a lot, you know, over the years, discussion with collaboration with our in-house theorists at Cornell, as well as Liang Fu and also Chen Ke at UCSB. And the HBN crystals are from the famous Japanese group. And yeah, these are the funding source. And thank you for your attention.
Okay, we have time for questions.
I just want to extend Leon's question a little bit. I didn't know that I could interrupt. I was politely sitting. So that's, oh, this is just, you know, age. So first part, this is the first part of your talk. Second part, you and I talked a lot. So you take a Mott insulator, which in the language of this community, half filled, but we call it filling 1, and you dope it slightly. What do you have from resistivity measurement, where you're seeing all this spin-phonon physics? Is the system resistance-wise a metal or an insulator? I suspect an insulator, which I would say is an Anderson insulator, right?
So actually, when there is a small range here between 0.8 and 0.9 something,
yes.
That it is actually, we can measure it, it's pretty much like a metal.
It is a metal.
Transport, yeah.
Okay, good. So then what you have then, you are saying you are seeing the spin-phonons in a metal, in an antiferromagnetic metallic background. That is kind of a very strange object, right? I mean, so when you go closer to the half filling, what happens? You have an insulator. Does the physics completely go away? That's what I'm actually asking.
Oh, so that, I mean,
no, it's a ferromagnetic metal. It was an antiferromagnet before, but the question is that the moment you dope,
I think it's antiferromagnetic at 0 field, right?
No, you have a 120-degree antiferromagnet at half filling. you are talking about the presence of magnetic field, but zero field.
Zero field is probably
first talking about
antiferromagnetic if you go to low enough temperature, which we can do. We can do in.
So in the regime where you don't have spin-phonon, low filling, you apply a magnetic field. What happens is what I'm asking. In the regime below this regime where you see spin-phonon, where the filling is very low, where if you didn't have a magnetic field, it would be Nagaoka physics, okay? Like if you could have infinitesimal doping. What do you see there is what I'm interested in.
Well, at least, you know, from the Curie-Weiss temperature, it's just that you dope further. So this only between 0.8 and 1, it is spin-polaron, right? And finally, you just get to like a very small exchange energy scale because they are just miles apart, right? The local moments. And so this is just very small, but there are some complicated dependence in the middle.
It's
so
not clear what's going on.
We don't know. Yeah, we don't know how to explain all of those. Yeah.
Okay.
Some version of Shankar's question, but slightly different way. About plateau. You are not exactly at half filling. So question is this: if you are at t equal to 0, is it a true plateau, or you expect that there will be fluctuation effects that will basically make situation look like plateau, but never sharp one?
The T is the temperature, right?
T is the temperature, yes.
There are too many T's here. What we believe is actually that this is, wow, I mean, this is as good as we can get in an experiment as a plateau. What we believe, what limits this is most likely the finite temperature effect. Because, you know, we do a temperature dependence, it completely disappears at about 5 Kelvin. The lowest temperature we can reach is 1.6 Kelvin. So we believe it will get sharper if we just decrease the temperature further. Yeah.
Yeah, quick question. So for the ferromagnetic insulator, you showed the RXY is quite large, 15 kilo.
Yeah.
But do I understand correctly, RXX is even larger, so that you call it a...
RXX is very large. It's an insulator, right? It's an Anderson insulator there.
Okay.
Yeah.
Thanks.
Yeah. It's actually not, it's not a Chern insulator. Yeah. It's RXX.
That's what you mean by understanding.
That's what we mean. But it's not, it has correlation also. Yeah. Yeah.
Can I ask about your second to last slide? I think it was the one where you're showing this one. Yeah, wonderful. Thank you. So in the left-hand region, in the upper panel, there are these black dots, okay, showing, I guess, tracking the Curie-Weiss temperature.
Yeah.
Right. So what's the temperature, or do you know the temperature at which the zero field anomalous Hall effect sets in? Is it the same temperature or much lower?
Oh, you mean, yeah.
So
for instance,
in the bottom panel, you plot this delta RXY.
Actually,
so,
yeah, it's probably like you can compare like this, right? Because this is like
okay, that's
a different temperature.
Yeah.
So when you get to very like close to 5%, the temperature is 0, essentially, right? The anomalous Hall set in starting from 0 temperature almost, because this is actually measuring down to 10 milliK.
That's sort of the temperature that you would, if you were to assign a Curie temperature, would have been
so basically
there,
the Curie temperature around here, Curie-Weiss temperature is way higher than the anomalous Hall set in, right?
Right, yeah.
Only maybe around here.
Is the trend continuously down, or does it go up and then down, or what?
This thing?
If you were to assign a quote Curie temperature, and how it varies between x equals 0
Oh, you mean
and x
like the
equals
ordering
0.5.
temperature? From
Exactly, yeah.
We have to, I think, so the thing is that we cannot measure below here because it's becoming too resistive, the sample. As far as we can tell, the temperature goes up continuously from 0 and then maybe peaked around here, but we don't know what's going on, you know. Then we can only rely on the Curie-Weiss fit below that, yeah.
Yeah, great, thank you.
Yes, very nice talk, so thank you. One question is, I mean, one thing we showed is that if you further frustrate the kinetic energy by adding second neighbor hopping or third neighbor, you can get bipolars. So basically a bound state of 2 holes and 1 spin flip. So is there any way of controlling that, you know, I mean, generating further neighbor hoppings?
The only way I can think of is tune the twist angle, possibly can tune a little bit of that. And I sort of believe that there is some effect from next nearest neighbor hopping, but I don't know how strong the effect is. So it's hard to say, you know, quantitatively. Yeah, but yeah, But what you would expect for like a bipolaron that?
Well, these are strange Cooper pairs, right? This is basically a bound state of two fermions and one boson.
Mm-hmm. So we probably.
So if they condense, they will give you superconductivity.
I should probably take a. You have a reference of something that.
Yeah, it's the same.
T2 to T1 that you probably.
Same paper that you are citing.
Oh, okay, all right, yeah. That means I didn't read carefully.
So I have two questions. So one is there any spin-orbit interaction now in the system?
Yeah. Yeah, actually, you need the spin orbit to get to a single.
I know,
band
but that doesn't mean that the effective model has strong spin-orbit interaction. That's a different question.
The effective model actually has near SU2 symmetry, as far as we know, for the valley. Actually, it's a pseudo-spin that is nearly SU2 symmetric.
So this will also answer this plateau question, to what extent we have a true plateau. There's a lot, but to what extent SC is conserved.
Yeah, actually, the spin is actually Ising-like spin, and the magnetic field can only couple to the Z component. It cannot couple to the in-plane component.
Yes, so I have a second question that was, can you use, so you gate the system with these electric fields, or can get the system with the electric fields. Can you also do now spectroscopy on this electric fields? So sending in some gigahertz or terahertz or whatever radiation, then do spectroscopy on that?
You want to, we thought about this like, apply instantaneous electric field. Maybe we can just instantaneously invert the band to, do something fun with the dynamical phase transition or something. Yeah, but it's certainly possible. Yeah.
Okay.
Yeah.
Cool.
So yeah, beautiful work. I'm a bit confused about your statement of heavy fermion with ferromagnetic interaction. So do you identify, Kondo interaction?
Actually, what I mean is that it has a positive Curie rise temperature. Yeah, it's like a heavy Fermi liquid with a positive Curie rise temperature.
Oh, okay.
Yeah. So
you don't mean Kondo here?
No.
Just in heavy mass and
heavy mass and local the net local moment interaction is is ferromagnetic. That's what I mean. Yeah.
You don't see any signature of Kondo.
You mean heavy fermion? You mean heavy fermion?
Yeah, or it's a Kondo coupling.
Yeah, we actually see it. I didn't talk about this. I can show you the result that the evidence we see the heavy fermions. Yeah.
Thank you.
Okay. So just some very basic question that's not immediately relevant, but when you have these ferromagnetic states, I mean, you have to set up an imbalance between valleys. And it happens somehow, a system finds equilibrium, but do you know what's the kind of the dominant process that actually takes a hole from one valley to the other? You know how they get there? The system wants to be ferromagnetic, but it starts out paramagnetic.
I thought you were supposed to tell me.
I don't know. Usually the experimentalist understands the microscopics better than anybody else. I thought I can ask.
Actually, I was, when I was preparing the talk last night, I was looking at your paper again, and it seems it's actually quite relevant. Then I tried to dig up some data to see whether we could see some possible magnetization plateau. It seems maybe, but it's a 1.6K measurement. It's for the optics, the transport, we can go to much lower temperature. So I'm not confident to say that whether there are actually some role of thin polaron.
But this is a separate question from our model, which is, is basically using Hubbard model formulation.
Yeah.
It has to do with in the Hubbard model, the spin is conserved, total spin is conserved. So you ask in reality, of course, it's not. I mean, as Achim's asking, and, so how does if I could ask a reverse question. I look in a regime of the phase diagram where the system wants to be paramagnetic, but I excite it with circularly polarized light, and I create an imbalance, a lot of K valley electrons. How do they get back to the K prime valley?
That part I could, so it's actually the excitons, and it's the exchange interaction of the excitons in the two valleys that cause the valley relaxation. That's the dominant. That is, as far as we know, for a single layer TMD, that is the dominant channel. That relaxes the valley if you pump by circularly polarized light.
But the momentum has to go somewhere, doesn't it?
Yes. Yeah. Then
Okay,
I
so
think you're
it's
more
really a
interested in the question of
multi-electron hole
if
process.
you have like a itinerant, right?
Yeah.
You have a population imbalance for the itinerant.
That's harder, right? If you just have only
Then you need an
polarized,
atomic scale defect, right, to mediate.
maybe it happens at the boundary or something.
No, but we must have this kind of atomic defects in the system. That density is about 10 to the 11 per centimeter square. Moiré density is 5 times 10 to the 12. You can sort of convert it's 2 to 3% of the Moiré density, right? So it's
I
not,
see.
yeah,
Okay.
it's not insignificant.
It's not that low. Yeah. Thanks.
I have a quick comment so that I can be responsible in the future. This is your first slide. You mentioned superconductivity. Let me make a prediction. You'll never see superconductivity in this material. The reason is superconductivity in graphene arises from electron-phonon interaction. It's well established. We established it. And electron-phonon interaction is extremely weak in TMD. I spent like 6 months talking to material scientists. It's like, a factor of 100 weaker. So no superconductivity. And in the future, if you see superconductivity, I have to eat my words.
Yeah, he definitely has.
We'll still try.
Well, I can be held responsible, as I said.
Okay, we need to move on.
Okay, all right.
But thank you for all your questions, and you can talk to the speaker.